In this experiment, you will be studying density. Density is defined as the mass of a substance per unit volume of a substance. A typical unit for density is grams per milliliter or grams per cubic centimeter. Cubic centimeters and milliliters are equivalent. Two objects with the same volume and different mass can be described as having different densities. For example, a cube of steel and a cube of polystyrene with the same volume would have different masses. The polystyrene cube would have less mass and therefore be less dense than the steel cube. Density is an intensive property, meaning that its value for a given material does not depend on the amount of material. A few examples of intensive properties include density, color, and boiling point. Extensive properties, such as mass and volume, depend on the amount of material present. Some intensive properties, like density, can be used to identify unknown samples. In this experiment, you will find the density of soda to determine the concentration of sugar in soda. It is difficult to directly measure the amount of sugar in a sample of soda, but it is relatively easy to measure the density of a sample of soda. Soda is a solution containing mostly sugar as a solute in water, the solvent. As the amount of sugar in a solution increases, the density of the solution increases because sugar is more dense than water, and the more sugar a solution has, the greater its density. For this experiment, you will determine the density of solutions of known sugar concentrations and construct a calibration curve from your data. Once you have determined the density of the soda, you will be able to calculate the concentration of sugar from the calibration curve. In order to calculate density of sugar solutions prepared in this experiment, measure the mass and volume of the solutions. In general, volume measurements are limited in accuracy by the tools used to measure them, such as graduated cylinders or rulers. Mass measurements are superior because analytical balances can measure mass to 3 or 4 decimal places. In order to make volume measurements in this experiment more accurate, you will determine the exact volume of a 25 milliliter Erlenmeyer flask with a ground glass stopper. Note that the exact volume will not be 25.00 milliliters. Once the exact volume of this container is determined, it can be filled with other solutions to that exact volume. In order to do this, you will fill the flask completely with deionized water and measure the mass of water in the flask by difference. Once you know the mass of water in the flask, you will use the known density of water at room temperature to calculate the exact volume of the flask with more significant digits than you would using a graduated cylinder. After measuring the mass of the dry flask with the stopper, you must fill the flask completely with water. The same flask should be used for all your measurements. Begin by filling the flask up to the lip with deionized water. Next, you should bring the flask to the sink. In this case, we're using a beaker to represent the sink, but you should actually go to the sink. And then you're going to insert the stopper into the flask so that the water displaced pours into the sink. Finally, dry the outside of the flask with a paper towel so that the mass of the water on the outside of the flask doesn't affect your results. A common mistake people make is trying to fill the flask up to exactly the 25 milliliter mark. It is nearly impossible to fill it up to the exact same spot, so that's why we use the displacement method. Another common mistake is leaving air bubbles in the flask. Air bubbles also affect the accuracy of your results, so you should be sure that there are no air bubbles in your flask. Finally, make sure you make all your mass measurements with the stopper placed in the flask. The density of a substance can be used to calculate either the mass or volume of the solution as long as you know the other variable. In this experiment, you will use the density of pure water to find the volume of the Erlenmeyer flask based on the mass of the solution in the Erlenmeyer flask. In this case, we need to know the density of pure water at 23 degrees C. You can look this up in your lab manual. The density of water at 23 degrees C is equal to 0.9975 grams per milliliter. This allows us to write an equality that says that in 1 milliliter of water, there should have a mass of 0.9975 grams. We can use this equality to calculate either grams of water to milliliters of water or milliliters of water to grams of water. In this problem, we want to convert the mass of water to the volume of water. In order to convert 26.604 grams of water to volume of water in milliliters, we can use the density equality such that grams cancels out. So we want to make sure that grams is on the bottom of our equality and milliliters, which is the unit we want, is on the top. So 1 milliliter of water has a mass of 0.9975 grams. When you do this calculation, you should get that this mass of water should equal 26.67 milliliters. You will use this calculation to determine the exact volume of your specific 25 milliliter Erlenmeyer flask and stopper. You should use the same flask throughout the entire experiment. You will use this volume multiple times to calculate the density of standard solutions and the unknown solutions later in the experiment. In order to construct your calibration curve, you will need to prepare several standard solutions of known concentration of sugar in water. To start your solutions, you need to make a stock solution 100 grams of 17% by mass solution from solid sugar. You can rearrange the mass percent formula to solve for mass of sugar. The mass of sugar is equal to the mass times the mass of the solution divided by 100. Now you can plug in the values you need. So your mass percent is 17%. You want to make 100 grams of solution, and you're dividing this by 100. When you solve that, you get that equals 17 grams sugar. When you make your solution, you probably won't have exactly 17 grams of sugar in it, but you will have around 17 grams of sugar. So make sure you calculate exactly how much sugar you add. So the mass of sugar that you add to make your actual solution is just the mass of the flask you use plus the sugar minus the mass of the empty flasks. In this example, when we added the sugar to the flask, the total mass was 113.305 grams, and the mass of the flask alone was 97.036 grams. So that means our solution will be made with 16.269 grams of sugar. The mass of solvent is equal to 100 grams minus 16.269 grams, which was the mass of sugar we've already added to the flask. So we need about 83.731 grams of water. Since it's easiest to measure water in terms of volume, we can convert the mass of water into the volume of water using the density of water at room temperature. 83.731 grams of water times 1 milliliter over 0.9975 grams is equal to 83.94 milliliters of water. So we must add approximately 84 milliliters of water to our flask to make the 17% solution. Once you add approximately 84 milliliters of water to the flask and swirl to mix the solution, you need to find the final mass of the solution. So the mass of the solution is equal to the mass plus the solution minus the mass of the empty flask. So in our example, the mass of the solution equals 202.388 grams, which was the mass of the final mixed solution and the flask together, minus the mass of the empty flask, which is 97.036 grams. The final mass of the solution is 105.352 grams. The last calculation you need to make for this solution is to find the exact concentration of this solution using the mass of sugar you added and the total mass of the solution. So the mass percent equals the mass of sugar divided by the mass of solution times 100. So we added 16.269 grams of sugar, and the total mass of our solution is 105.352 grams. We're going to multiply that by 100. So our final answer is 15.443% sugar. Once you prepare the stock solution, you can dilute it to prepare the other solutions needed for the calibration curve. You can use the dilution equation to figure out how much of each solution you need. So the dilution equation, if you remember, is C1V1 equals C2V2. So the concentration of our stock solution is 15.443%, and we need to know the volume of that solution. We need to dilute to prepare a 10% solution and 50 milliliters of it. When you solve this, you should get that the volume of the stock solution we need is 32.377 milliliters. You will use approximately 32 milliliters of the stock solution and 18 milliliters of water to make 50 milliliters of the 10% solution. When you make the solution, you may not use exactly 32 milliliters of the stock or exactly 18 milliliters of water. To determine the exact concentration of the 10% solution, you will need to know exactly how much of the 15% solution you added and exactly the total volume of the solution. So to find the concentration, we can use the dilution formula again. C1V1 equals C2V2. In this calculation, we still have our 15.443% solution, and we added 31.9 milliliters of that solution. We are trying to find the exact concentration of solution 2, and our total volume of solution is 50.4 milliliters. When you solve this, C2 is equal to 9.77%. So approximately 10, but exactly 9.77%. You will repeat the calculations above to prepare a 6 and a 3% sugar solution from the 15.443% stock solution. Once you've prepared your sugar solutions, you must measure the density using the 25 milliliter Erlenmeyer flask. Here I have my 17% solution. I will rinse the flask first with several milliliters of the solution to be sure there's no water left on the inside of the flask. You should repeat this a couple times before making your measurement. Once you have rinsed your flask several times with the solution, you should fill it up to the lip. Once you have filled your solution to the lip, over the sink, displace the solution with the stopper again. You should always fill your solutions over the sink so that you don't get sugar solution all over the bench tops, because everything will get sticky.
Next, rinse the outside of your Erlenmeyer flask with water to remove any solution left on the outside of the flask. Finally, dry your flask with a paper towel. Once your flask is dry, you can measure the mass of the flask and then dump it out and do your next solution. You should use the same flask throughout this entire experiment. You will repeat this process for all your solutions. Be sure that you rinse the flask again with each solution prior to finding the density of the solution.
Now that you've determined the mass of each solution and the exact volume of the flask, you can calculate the density of each solution. Then, using concentration and density of the solutions, you can construct a calibration curve to determine the concentration of sugar in the unknown sample. Because you are completing the same calculation multiple times, it is easiest to set it up in Excel. For each solution, I have already entered the mass of the solution in the stoppered Erlenmeyer flask. Then, in the next column, I entered the mass of the dry stoppered flask without any solution in it. This is the same for each sample, so you can drag the value down the column by clicking on the value and holding your cursor in the bottom right corner. When you see a solid black plus sign, you can click and drag the mouse down to fill in the values. In the next column, you will enter a calculation to find the mass of the solution alone. Start by selecting the cell you want the calculation to be in, and then typing the equal sign. Then use the mouse to select the mass of the solution in the flask. Then type the minus sign, and select the mass of the flask alone, and hit Tab. This will do the calculation to give you the mass of the solution alone. You can copy the calculation like you did for the mass of the flask by selecting the black plus sign in the lower right corner and dragging down. This will copy the calculation throughout the column. Now you have all the values you need to calculate the density of the solutions. Recall the density of the solution is equal to the mass of the solution divided by the volume of the solution. In order to calculate it, first type equal sign in the cell that you want to do the calculation in. Then select the mass of the solution. Then type / and click the volume of the solution, and then hit the Tab button. This does the calculation for density. You can copy the calculation like you did previously by dragging the cells down, and all the values for density should fill in. In order to construct my calibration curve, I'm going to collect my data that compares the sugar concentration and density of my standard solutions. As you can see, I've inputted the concentration of the solutions I prepared, and now I'm going to copy the density of those solutions into the next column. When I select my data and select copy, I want to paste my data here, but I only want to paste the values and not the calculations. So choose values under paste options, so you just paste in the numbers. Now you can construct a calibration curve that relates your sugar concentration and density data. Select the data you wish to graph, and then choose the Insert tab and find the scatter plot. Once the chart is in your worksheet, choose the quick layout that displays the chart title and axis title. Once you have labeled your graph, you can add a linear trend line. Right-click on any of your data points and select Add Trend Line. The Format Trend Line box opens, and make sure that it's selected for the linear trend line. Scroll to the bottom and click Display Equation on Chart and Display R² Value on Chart. Then close the trend line option box. So now you have the equation of your line and the R² value, which tells you how well your data fits the line. Once you've made your calibration curve, you can determine the concentration of an unknown using its density. You should place your unknown solution in the same flask you used to measure the density of your standard solutions. Enter the mass of unknown solution in the flask in the box here. Once you've determined the mass of the solution in the 25 milliliter Erlenmeyer flask, you can use your calculations from your solutions to find the density of the solutions. Simply click on the last box of each row, find the black plus sign, and drag the values or calculations down. So when we get to the last box, we can find that the density of our solution is 1.046. Once you have found the density of the unknown solution, you can use the equation of the trend line from the calibration curve to calculate sugar concentration. In order to do this, you can set up a calculation. Type the equal sign and open parentheses. Your y value is the density. So click on the density of the unknown solution, type minus 0.9972, and then close parentheses. Type / 0.0044 and hit the tab button. The sugar concentration in your unknown sample is about 10.97. You should report the sugar concentration in your unknown sample to the correct number of significant figures. The volume of the solution and the density of the solution both have 4 significant figures, so our answer should have 4 significant figures in it. Select the concentration of your unknown and use the decimal place arrows to round your answer to 4 decimal places. Your final answer should be 10.98. When preparing solutions, it is important to quantitatively express the concentration or amount of solute in a given amount of solvent. In this experiment, you've already expressed concentration in terms of mass percent. Another important concentration unit is molarity, denoted big M. Molarity is the number of moles of solute in exactly 1 liter of solution. To calculate molarity, you need the number of moles of solute present in the solution and the exact volume of the solution. In this experiment, you will convert the percent of solutions into molarity. In order to do this, we need several conversion factors. In order to convert the mass of the solute to the moles of the solute, you must know the molar mass of the solute in grams per mole. In order to convert mass of solution to liters of solution, you must know the density of the solution in grams per milliliter. When converting values given in terms of percent, like mass percent, you may need to choose an arbitrary value in order to do calculations. For example, if a solution is 12.1% by mass sugar, it would be easy to use 100 grams of solution as the arbitrary value, since any percent is the part divided by the whole times 100. If you choose 100 grams of a solution, the amount of sugar in that solution is 12.1 grams. This greatly simplifies calculations using percentages. Now we can convert the concentration of a 12.1% by mass solution of sugar to molarity. We know that molarity is equal to the moles of sugar divided by the liters of solution. So what we need to do is convert the grams of sugar and the grams of solution to moles of sugar and liters of solution. We should use the relationship that 100 grams of solution is equal to 12.1 grams sugar. We get this relationship from the mass percent, and we've chosen 100 grams of solution to make our calculations simple. So let's begin by converting 12.1 grams of sugar to moles of sugar. In order to do this conversion, we need an equality. The equality we need is molar mass. That relates moles of something to the mass of something. In this case, the chemical compound of sugar is sucrose, and the molar mass of sucrose is 342.30 grams. Since we would like to cancel out grams of sugar, we'll use that part of the equality on the bottom and the moles part on the top so that our final answer will be in moles. So 1 mole of sugar over 342.30 grams sugar is the equality we need for our calculation. When we multiply and then divide, our answer should be 3.5349 times 10 to the negative second moles sugar. So this is the value we need in the top part of the molarity value. Next, we will convert mass of the solution to liters of the solution. So if we take 100 grams of the solution we need 2 equalities to do this calculation. The first equality we need is the density. The density of the solution relates mass of solution to volume of solution. In this case, we want to get rid of the mass of the solution, so that part of the equality will be on the bottom, and the volume part of the equality will be on top. So 1 milliliter of solution over 1.051 grams of solution, which is the density of this particular concentration solution. Now, since we need our value in liters and not milliliters, our second equality relates liters to milliliters. In this case, there's 1,000 milliliters in 1 liter, and we want to get rid of milliliters. So we put this value on the bottom, and we have our 1 liter on the top. When we put this into our calculator and solve it, we should get 9.515 times 10 to the negative second liters of solution. This is the second value we need to calculate the molarity. Now that we've converted the mass of sugar to moles of sugar and the grams of the solution to the liters of solution, we can calculate the molarity of the solution. So, since we know the moles of solution is equal to 3.5349 times 10 to the negative second moles, and the volume of that solution is equal to 9.515 times 10 to the negative second liters of solution. When you plug these values into your calculator and divide, you should get that the molarity of the solution is 0.372 molar, taking into account the sig figs from the original value of 12.1%.